Okay, in this video you should have watched the theory behind the first order transient analysis of first order circuits rather. So that's RC or RL circuits, and in this video we're just going to work through some various examples. In this first example we have an RL circuit with a dependent source in it that is a voltage source dependent on the current through the inductor. In this problem, we have an initial condition that the inductor current is 10 amps at time 0, and we want to find an expression for the current through the inductor for time greater than or equal to 0 seconds, and the current through the 2 ohm resistor for the same time interval. So again, we follow the same procedure for all of these circuits. First, we are going to determine the initial condition of the inductor or the capacitor. So in this case we have an inductor, and our initial condition that we care about is IL at time 0, instant before the switch. In this case we don't have a switch, it's just initially charged, and we tell you whenever it's connected to the circuit. And that's what we defined as I. So I0 is 10 amps. Next, we find our final condition. So that's IL as time goes off to infinity, which is I as time goes off to infinity. We assume infinity because we're assuming this circuit eventually goes to steady state conditions again, no more changes in time. Likewise, if I go backwards, 0 minus is the instant before a switching event occurs and the inductor is connected to the circuit as shown here. So in other words, this is steady state. From 0 onward, we're in transient. Okay, so anyways, back to our final condition. Since there are no independent sources in this circuit, it must relax back to 0, so our final condition is at 0 amps. So we know the inductor starts at 10 amps and will relax to 0 amps. And the next thing we need to do is find the time constant for that exponential decay. That time constant for an RL circuit is the inductor over the equivalent resistance seen by the inductor. Okay, so for finding the equivalent resistance seen by the inductor, we need the following circuit. So we pull the inductor out. The inductor is thought of as the load here, and we want the equivalent resistance seen by the terminals of the inductor. Note, we have a dependent source in this problem, so we can't use resistor reduction. So we must use source driving technique. So I'm going to connect an independent source to those nodes. I'm going to actually make it go downward and call that 1 amp. I'm going to make that downward because I just becomes equal to 1 amp here. And this voltage source becomes 3 times 1 or 3 volts. Okay, so now to analyze this, what we're looking for is the equivalent resistance is given as the voltage VSD across that current source divided by the amount of the current, which is 1 in this case. Okay, so to analyze this, if I do a KCL, well, first I need to choose a ground node. Let's choose this top node to be my ground such that this bottom node becomes V sub SD. I get to do KCL at V sub SD. I get 1 amp coming in through this branch, assuming current is going out through the 2 ohm. I get equal to VSD minus 0 over 2. Assuming the current is going out through this path, note that this node above the 3I voltage source is VSD plus 3, so that current will be given as VSD plus 3 minus 0 over 4. Solve this, and I get VSD is equal to 0.33 volts, and R equivalent is therefore 0.33 ohms. And finally, based on this, we can write that tau is 0.5 henries over 0.33 ohms, or 1.5 seconds. Okay, so now that we found our boundary conditions, we found that the initial current was 10 amps, the final current goes to 0 amps, and our time constant is 1.5 seconds. We fill in the expression for the current through that inductor, which is what we define as I, as a function of time, equals the initial minus the final, times e to the minus t over tau, plus the final. Subbing those in, we get 10e to the minus 2t over 3 amperes. Okay, so now that we found the inductor current, it's a known quantity in our circuit, and we can use any analysis technique that we want to solve for any other parameters, such as Ix. Nodal analysis, mesh analysis, whatever. This provides us a known now. In this case, we note that the inductor is in parallel with the resistor, the 2 ohm resistor that we're interested in, so those voltages must be the same. We'll label that V sub L. And noting that we can find V sub L directly by noting the relationship for I and V of an inductor as being L, V equals L times DIL over dt. Specifically, that's 0.5 henries times the first time derivative of the current that we found in the first part, which is 10e to the minus 2/3 t. Performing this computation, you get negative 3.3 e to the minus 2t over 3 volts for the inductor and the resistor voltage. Following this, we can write that Ix just must equal VLT over 2 ohms, applying Ohm's law for the resistor, therefore equaling negative 1.67 e to the minus 2t over 3 amperes. So we found that the inductor current was 10 e to the minus 2t over 3, and the current through the 2 ohm resistor is negative 1.67 e to the minus 2t over 3. Likewise, from this, if you wanted to simply find the current through the 4 ohm resistor and dependent voltage source, you could do so by just performing a KCL expression. You know 2 out of the 3 currents. Okay, let's do another example. This time, instead of giving you the R and the L, or the R and the C, or another circuit, I'm going to give you the voltage and the current. Specifically, we're looking at the voltage across a parallel RL combination as 150 times e to the minus 50t volts, and the current is going through the resistors denoted in this chart as being 30 e to the minus 50t amperes. So, for part 1, let's find the inductor, the inductance of the inductor, and the resistance of the resistor. That would make this happen. So we have to think about what part of these expressions sets the inductance and resistance, and we note that when computing the tau, the time constant of the LR circuit, we know that tau was L over R, and our expression always included e to the minus t over tau. Therefore, tau must, which equals L over R, must equal 1 over 50. So one constraint is that L over R must equal 1 over 50. That's only part of the constraint here. We just know the ratio is 1 over 50. So for part 2, well, let's look at the initial and the final conditions of the problem. We know that the final value of the current must be 0 because there's no independent sources present in the problem. Therefore, we know the expression for the current through the inductor is going to equal the initial current times e to the minus t over tau. Therefore, since this equals 30 e to the minus 50t, I naught must equal 30 amps. We also know that the initial voltage V at time 0 equals 150 volts. This is the voltage across both the resistor and the inductor. So using Ohm's law, we can see that the initial resistance must be the initial voltage divided by the initial current. So 150 volts divided by 30 amps. In other words, that's 5 ohms. Therefore, since L over R equals 1 over 50, we can write the inductance as being R times 1 over 50. Therefore, the inductance computes to being 0.1 henries. All right, in part 2, let's compute the initial energy stored in the inductor. Okay, omega L at time 0 is given as the energy in an inductor is related to the current as 1/2 the inductance times the current squared, and here specifically we are looking at the initial current, so it's not changing in time, so we don't have any of those exponential functions tacked in here. So it's just simply 1/2 times 0.5 times the initial current, which is 30, quantity squared, computes to 45 joules initially stored in the inductor. Now we know that once that's connected to the resistor, the energy stored in the inductor will begin to be dissipated by the resistor. So let's compute something about that. So specifically, let's look at the fraction of the initial energy, which is this 45 joules, that's been dissipated after 10 milliseconds connected to the resistive load. So we know the energy dissipated by the resistor is going to start at 0 but rise up to the final value of 1/2 L I naught squared. So the function is given as 1/2 L I naught squared times 1 minus e to the minus 2t over tau. Okay, so 1 minus e to the negative 2t over tau is the function for a rising exponential to final value of 1/2 L I squared. So the energy dissipated after 10 milliseconds would be given as 1/2 times 0.5 times 30 squared times 1 minus e to the negative 2 times 10 milliseconds times 50, or divided by 1 over 50. So that energy works out to be 28.45 joules dissipated at 10 milliseconds. So the percent dissipated then, simply given as 28.45 divided by 45 times 100%. We could do this as a fraction as well, like I actually asked for. Either way, this works out to be 63.2% of the total energy has been dissipated after 10 milliseconds. Okay, I thought we could visualize what we're talking about here. So the initial energy stored in the inductor was what we called 1/2 L I naught squared. So that's shown here, it's the red dot. We're going to plot the energy stored in the inductor as a function of time. Looks like this function. Okay. So this function works out to be 1/2 L I naught squared times e to the minus 2t over tau. If we look back at our theory for the decaying function of both voltage and current and compute the energy out of that. So the energy dissipated by the resistor, though, so the energy is being transferred from the inductor to the resistor, starts at 0, rises as an exponential function towards a final value of 1/2 L I squared. And that function is given as 1/2 L I squared times 1 minus e to the minus 2t over tau. So kind of remembering this visual is how will help you figure out what you're being asked. So if it's how much energy being dissipated by the resistor or how much energy is being stored at the inductor at time t.